All right, chapter 7, section 8. We're going to do parts 1 and 2 together because they are really concepts that we've seen before, just with a different parent function. So graphing square root and other radical functions. Did you know the inverse is the function's reflection across the line y equals x? So in the last lesson, we did see that, when you're finding the inverse of the function, it's all about switching the x's and the y's. And in fact, when we graph the function and its inverse on the same coordinate plane, you will see a reflection across the line y equals x. And we're going to do that right now. So it says graph y equals 2x minus 1 and its inverse. All right, well, let's first graph y equals 2x minus 1. So we're going to plot the y-intercept at -1. Slope is 2, so we rise 2, run 1. Again. And we keep doing this so we can get a good straight line. And I'm going to take a straight edge and connect those points. So you will need graphing paper. And make sure you're putting arrows on your graphs, on your lines, okay? All right, now it says also graph its inverse. Well, we could potentially take all these ordered pairs that are on this function and switch the x's and the y's and plot those. But let's just, for the extra practice, find the equation for the function's inverse. So I'm going to let the y be an x and let the x be a y. I'm switching the x and y. I'm going to take the 2y minus 1 over to the other side. I showed you before I like to do that because I'm solving for y and I want that on the left side. I'm going to add 1, so this is 2y equals x plus 1. I'm going to divide by 2. Y equals x plus 1, that quantity divided by 2. I could break this apart and rewrite this, right? This is a 1 here, so this is y equals 1/2 x plus 1/2. 1/2 x plus 1/2. And since this is linear, it's a line, I'm going to then say f inverse of x equals 1/2 x plus 1/2. Now, in a different color, I'm going to graph this line. F inverse of x equals 1/2 x plus 1/2. So the y-intercept is 1/2. Got to be in the midway between. And then up 1 to the right 2, just like we did before in the last lesson. Up 1 to the right 2. And then from here, up 1 to the right 2. Up 1 to the right 2. Down 1 to the left 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 2. Oop. It would help if you went 2, not 1. All right, we'll just fix that. Pretend it never happened. Okay, so now I'm going to connect these points to draw the line of the inverse function. Right? This one is f inverse of x. And this function was f of x. Now, let's think about that line y equals x. Okay, so whatever y is, so is x. Or whatever x is, so is y. So ordered pairs on this, what we call the identity function, would be 0, 0, 1, 1, 2, 2, 3, 3, 4, 4, and with the negatives as well. So 0, 0, 1, 1, 2, 2, 3, 3, 4, 4, 5, 5, 6, 6, and so on. So it's this line that's like on the diagonal. All right, if you compare that red line with the purple line, you should see symmetry across this line, y equals x. Okay, so symmetry meaning, you know, I could identify this point right here, and I bet the coordinates of this point, I will make it darker with a green dot. This ordered pair is x is 3, y is 2. Look at this ordered pair, x is 2, y is 3. They are switched. And these 2 points are the same distance away from that line y equals x. Okay, so convince yourself that this is a thing. There's symmetry about the line y equals x. All right. Again, here we're going to talk about that the inverse may or may not be a function. Okay, this one happened to be a function, so we used inverse function notation. The x values and y values are switched with functions and their inverses. So the domain of the original function is the range of the inverse and vice versa. So not only do the x's and the y's switch in the tables, but whatever the domain is of the function becomes the range of the inverse. And whatever the range is of the function becomes the domain of the inverse. Okay, so everything switches. It's just all about switching. All right, now we have another one where we have a quadratic involved. And we saw something similar to this before. It says graph y equals x squared, and then find the inverse. And then we're going to graph that as well. So let's graph the y equals x squared first. All right, so let's do x and then f of x. Folks, this is the parent function. We shouldn't really need to show work for a table here, right? Because we know, you know, I'm going to put 0 in the middle. Well, let's just go backwards. -3, -2, -1, 0, 1, 2, and 3. The function is x squared, so this squared is 9, this one squared is 4, this one squared is 1, that one squared is 0, that's 1, that's 4, that's 9. Okay, we're going to plot these ordered pairs. X is -3, y is 9, x is -2, y is 4, x is -1, y is 1, 0, 0, 1, 1, 2, 4, 3, 9. Okay, and recall our parent function, the parabolas. We've graphed these before. All right, now we're going to find the function's inverse, and we're going to graph that. All right, graph y equals x squared, find the inverse. All right, let's find the inverse. So I'm going to let the y be an x equals y squared. I like y on the left, so y squared equals x. Take the square root, y equals plus or minus the square root of x. All right, we've got positives and negatives here. We know this is not a function, so I cannot replace the y with f inverse. It's not a function because of the plus or minus. That's a telltale sign that this is not, this inverse is not a function. It's an inverse, it's just not a function. All right, so x, y, inverse table. If this was a function, I would write f inverse of x here, but I can't do that. So what did we say before? You take the x's and the y's and you switch them. So this is 9, negative 3. This is 4, negative 2. This is 1, negative 1. Or just copy down. Okay, we got 0, 1, 4, 9. And here we have 0, 1, 2, 3. So the x's and the y's switch. Now notice on the y's, this is positive and negative 3. This is positive and negative 2. This is positive and negative 1. Why? Well, that's taking care of my plus or minus from this right here. Okay, the y equals positive square root of x, and then the y equals negative square root of x. Okay, so that's why we have positives and negatives on the y side versus over here we did not. All right, let's graph this. I'm going to again graph in that same red color. Let's graph 9, negative 3, 4, negative 2, 1, negative 1, 0, 0 is there, 1, 1 is here, 4, 2 is here, 9, 3 is here. If I turn this, you're going to see that this is a parabola as well. It's just sideways. It's opening up sideways. I'm going to turn it right side up. And we can see this does not pass, the red graph does not pass the vertical line test. Hence, it's not a function. We can then take it a step further and put in our little dots or our dashed line for that equation y equals x, right? To see the symmetry. A function and its inverse are symmetric about the line y equals x. Okay, and so if we compare and we look at, say, this point here and this one here, they are the same distance. In other words, if I would fold my coordinate plane on this dotted line, y equals x, this parabola would lie on top of that parabola. This point would lie on top of that point, that one on top of that one, this one here, and this one over here. So you see that symmetry across the line, or you should see the symmetry across the line y equals x. Again, this was my f function, and this red graph was my y equals plus or minus square root of x. I can't say that's my f inverse of x because the inverse is not a function. Okay, so all I did here was label this, and then I labeled this with y equals what the equation is, because again, it's not a function because it fails the vertical line test. And then this thing here at the bottom, it just says this is the parent function. Okay, it's the parent function of y equals x squared. It's the parent quadratic function. Now, this is going to lend us and show us what the square root function looks like, because we just graphed a square root function. The only thing is we graphed the top and the bottom. Okay, we graphed positive square root of x and we graphed negative square root of x. And guess what? This piece right here, this top piece, let's see if I have a yellow highlighter. I don't, but I can use pink. This piece right here is the positive square root of x function. And then this piece on the bottom, excuse me, this piece here is the negative square root of x. Okay, you're going to see that when we look at the square root parent function in just a few moments. Okay, if you have any questions on this, you know what to do. Please ask. I can't help you if I don't know you have a question. All right, side 2. Here's where we're going to talk about the parent function, the reflection, stretching, any translations. We've done this before, transformations of functions. Okay, and here we're going to look at square root case and then radical case. So, parent function, first things first, square root, y equals square root of x. Reflection, in the x-axis, that's going to be y equals negative square root of x. Folks, this negative flips it over the x-axis, and that's what this means. Stretching, well, that's when you have a number in front of this. Whether it's positive or negative doesn't matter because the negative means flip it. Y equals a, that's a stretch, or a shrink, times square root of x. It's a stretch if the number is bigger than 1. It's a shrink if it's a fraction or a number between 0 and 1. A reflection in the x-axis. Well, let's change that and say reflection in the x-axis with a stretch or a shrink. We want both because we already have reflection in the x-axis here. So y equals negative a times the square root of x. Translation, horizontal by h, vertical by k. Y equals the square root of x minus h, or y equals the square root of x plus k. When it's grouped inside with x, you move on x, left and right. That's your horizontal shifting. Your vertical is up, down. If it's not inside there with x, we mean to move it up or down on the y-axis in the direction opposite the sign. Don't forget about that. Combined. Combining a horizontal and a vertical shift, your equation would look like y is equal to the square root of x minus h, and then plus k on the outside. Now, again, I realize this looks a little abstract because there's no particular numbers here right now. But these are the models that represent any case. We will do actual examples in a few moments. All right, let's apply this now to any radical equation. Square root is its own, right? But we had cube roots and fourth roots and fifth roots and so on. Y equals the nth root of x. The only thing that's going to change here between this column and this column is the nth root. Y equals negative is the flip over the x-axis, and here we've got the nth root of x. Here we have y equals a times the nth root of x. Here we have y equals negative a times the nth root of x. Keep it on going. Next we have y equals the nth root of x minus h, and y equals the nth root of x plus k. And then finally putting the shifting, both shifts together, the nth root of x minus h plus k. All right, we'll do a couple examples. Example 2, we are going to graph the square root of x plus 4. There's no plus or minus here. You are not taking the square root. The square root is already given to you, and it's given to you as the positive case, because if it wasn't the positive case, there would be a negative sign in front of it. Okay, so we're going to look at this. We're going to say, oh, we're graphing y equals the square root function. Well, it really helps to graph the parent function, and it really helps to memorize the points on the parent function. Folks, and that's not too terribly difficult to do. The parent function is y equals the square root of x. So we want to pick x values that are perfect squares, like 0. Well, if x is 0, so is y, because the square root of 0 is 0. The square root of 1 is 1. The square root of 1, 2, 3, 4 is 2. And the square root of 9 is 3. Folks, this is the parent function. That's what it looks like, your square root function. Now we're going to take that square root function, and this says to do what? This is a translation. Move it up 4 units. It's not grouped in under the radical with the x, so that's an up-down shift. Plus means go up. So I'm going to take my 0, 0 and slide it up 4 units. This is 0, 0. This is 1, 1, 2, 3, 4, 2, 5, 6, 7, 8, 9, 3. Here is my square root function shifted 4 units up. This is the graph of y equals square root of x plus 4. This one here is parent function, y equals square root of x. All right, example 3. What do you remember about when it's inside there with x? Here we just said if it's not inside with x, we move up, down on the y-axis. Here, if it's inside with x, we move it where? You can look at the chart. That's a left-right move. Which way, though? Well, hopefully remember, you always move in the direction opposite the sign. This says take the parent function square root of x and move it not to the left but to the right 2 units. So let's graph the parent function first. It helps us, well, it helps me anyway. And it helps you to memorize those ordered pairs that are on it. 0, 0, 1, 1, 4, 2, and 9, 3. Why? Because 0, 1, 4, and 9 are perfect squares. And so the square root of them become integers. This is y equals the square root of x. And we're going to take that parent function and move it to the right 2 units. So all of these points get moved over to the right 2 units. So here, this one goes here, this one goes here, this one goes here. And let's look when I graph my red graph and call this y equals the square root of x minus 2. Folks, if this is 0, right, we learned it, we can move the 0, 0. So if I shift the 0 here, then this is square root of 1 is 1, square root of 2, 3, 4 is 2, 5, 6, 7, 8, 9 would be 3. Maybe I'm off a little bit over there, but I didn't have a grid. Okay, so if you have questions on these transformations, please let me know, or how to graph the square root. All right, which is now going to bring us to that 3rd page of notes, which is labeled 7-8 part 2, but it's really not part 2, it's just continuation. Okay, graphing, square root, and other radical functions. So I see that the first 3 examples 1, 2, and 3 are square root. This one here is not, though. So I'm gonna wait for this one. This is parent function, though, because there's no up, down, left, right. So this is we're gonna learn how to graph a cube root function, which is actually the inverse of a cube function. All right, so let's graph the parent function for examples 1, 2, and 3. All right, so again, parent function here is 0, 0, 1, 1, 4, 2, 9, 3, because square root of 0 is 0, square root of 1 is 1, square root of 4 is 2, square root of 9 is 3. 0, 0, 1, 1, 4, 2, 9, 3. So all I'm doing for these three is graphing the parent function. All right, we got all three of those. We're going to wait for this one because that's a different kind. You have to look at the index. You have to make sure you know what you're talking about. All right. This, my friends, is a stretch. We are not, we are not flipping this thing upside down. And remember, the stretch makes the y values bigger, or shrink makes the y values smaller. In this case, it's a stretch. And this makes the y values larger. All right, so we're going to say the square root of 0 is 0, but wait a minute, multiply it by 4. Well, it's still 0. The square root of 1 is 1. Now notice I'm covering it up with my finger. The square root of 1 is 1, but wait a minute, multiply that 1 by 4. We're up here. The square root of 4 is 2, but wait a minute, take that 2 and multiply it by 4 and get 8. The square root of 9 is 3, but wait a minute, multiply that 3 by 4 and get 12. So this is 10, 11, 12, somewhere up here. Folks, this is a stretch. It's kind of a big stretch, actually. And so my red graph here, let's put this, okay, this red graph, I'm going to do it in a different color so we can see it better. Not that we can't see it, but the arrow's getting bugged up there with that, the word larger. Okay, so this graph is my y equals a stretch times the square root of x. All right, so what you have to remember is the stretch. After you figure out, you know, square root of 1 is 1, but wait a minute, multiply by 4, so you got to go up. So it's stretching this thing up. This one here is simply the parent function flipped upside down. If you notice, if I cover up the negative sign, that's the parent function right there, the square root of x. We already have it graphed. This leading negative means flip them upside down. The square root of 0 is 0. Make it negative. It's still 0. The square root of 1 is 1, but wait a minute, make it negative, upside down. The square root of 4 is 2, but I have to be upside down. The square root of 9 is 3, but I have to be upside down. And there is the graph of my upside down square root function. Or we say reflect over the x-axis. All right, we did those first two examples. Let's talk about the domain of those two examples before we go on to the next problem. The domain are which values? They are your x values. Folks, none of the negative x's are found on the graph of this function. None of them. 0 is, I'm going to do the purple one now. 0 is on the graph of that function as an x value. 2 is on the graph of the function right here as an x value. 6 is on this purple graph way up here. Okay, so all the positives, including 0. So we start at 0 with a bracket and go to infinity. They're all all the x values from 0 on, none of the negatives. All right, let's look at the domain for the second one. What do you think the domain is there? Well, if you said the same thing, 0 to infinity, you would be correct. So why don't you pause the video and try example 3 on your own? Okay, hopefully you tried this one on your own, and we'll go through it. All right, this 2 means take the 0, 0 and slide it up 2 units. This plus 4 means slide it back left 4 units. And my point goes right there. Now this negative says I got to be flipped upside down. And this 3 says I need to stretch. So if this is tentatively my new 0, 0, and I say the square root of 1 is 1, but wait a minute, multiply by 3 and be upside down. So that gives me a point right here. Now I can say the square root of 1, 2, 3, 4 is 2, but 2 times 3 is 6, and I have to be upside down. 1, 2, 3, 4, 5, 6. And then the square root, remember this is 0, so this is 1, 2, 3, 4, 5, 6, 7, 8, 9. The square root of 9 is 3, but times 3 is 9 upside down. 1, 2, 3, 4, 5, 6, 7, 8, 9. And now I'm ready to connect my points with a smooth curve. Okay, so this red graph is my parent function shifted up 2 units to the left 4, stretched by 3, and reflected over the x-axis. The domain. Remember the domain or the x values? Where am I starting? Look at this point right here. I'm starting at -4 and going to positive infinity. The -4 is included. Okay, they take a little bit of practice, but you've done this before with stretching and shrinking. All right. It makes sense for cubes that we're going to pick x values that are cubes. Choose x values. We just got done with radicals. You should know which are our basic cubes. Choose x values that are cubes. 0 is a cube. 1 is a cube. 8 is a cube. 27 is a cube. 0, right? Cube root of 0 is 0. 1 is a cube, right? 1 times 1 times 1. 8 is a cube. 2 times 2 times 2. 27 is a cube. 3 times 3 times 3. And then, hey, guess what? On the other side, because it's an odd index, we can take the cube root of negative numbers. Okay, that's probably all about we need for this. The 27, it's going to be off the grid, so we're not going to use it. And now we're going to plot this. These are my x values, okay, x's. We chose cubes. Cube root of -8. All right, let's put -8 here. Cube root of -8 is -2. The cube root of -1 is -1. Cube root of 0 is 0. The cube root of 1 is 1. The cube root of 8 is 2. And so your graph takes on this kind of like an S-like shape. And now I want you to guess what the domain is. Notice the arrows. Domain are my x values. We are going from negative to positive infinity. Okay, so let me know if you have questions on the domain. Let me know if you have questions on graphing. Make sure that all of your graphs go on graphing paper. If you need some, please ask or just take some off the table. I always have it in class. You You can also print some offline. I have them in the folders in your resources folder. Have a great day.